Qichen from NetEase Hangzhou Network Corporation. Here I will present our approach for the Text 6 in DCASE challenge. The title of our paper is Automatic Audio Captioning with Weekly Supervised Training and the Word Selection Method. This is an outline of this presentation. Let's start with introduction and motivation. Automatic audio captioning is a translation task from speech to text. Compared with speech recognition, this task gives a description of the audio rather than a transcription. Compared with audio tagging, this tag needs to extract more detailed features from the audio. Our motivation has the following 2 points. The first point is pre-training on the large dataset, followed by fine-tuning on the target dataset boosts performance. The second point is similar audio may have similar captions. It can help to generate a better caption. We try to introduce 2 types of similar information. One is tag level. We use the audio tag generated by PNN to assist in decoding. Another is the caption level. We use keywords extracted from the captions of similar audio to assist in decoding. This figure is the overview diagram of our proposed method. We use CN14 architecture in PNN as our encoder and a 2-layer transformer as the decoder. In the pre-training stage, the parameters of encoder are frozen and only train the decoder. In the training stage, the encoder parameters are unfrozen and trained together with the decoder. In the first 2 stages, we use all data to train the model. In the fine-tuning stage, only use the closed dataset to fine-tune the model. We use 3 methods for data augmentation. First is perturb audio data. Use speech perturbation and reverberation. We perform a 5-fold augmentation of closed data. Secondly, we add the audio caps dataset to the training dataset. Besides, we design a method to construct weekly label data from the internet. We collect audio and the description from the free sound effect site. Then, we use the heuristic rules to filter and clean captions. Finally, we remove audio shorter than 5 seconds and randomly select 50 to 30 seconds of clips from the long audio. Using this method, we collect 65,000 audio clips and captions. There are our heuristic rule and an example. We use templates to extract candidate captions. Then we remove noise word and filter the unregistered word in the caption. Next, we will try to introduce tag level similarity, which is tag enhanced decoder. We use PNN model to pre-train the tag of each audio in the dataset. In the training stage, we use the tag as the label and place it in front of the caption. We require the model to generate the tag and the caption. As shown in the figure below, we add the tag as known information to the decoding in the test stage. In addition to similarity of tag level, we also try to use keyword enhanced decoder to introduce caption level similarity. With enhanced LSTM for natural language inference, we designed the network as shown on the right. It uses PNN as an audio encoder and gets a 2045 dimension feature sequence. Then, we treat each audio feature sequence as the word embedding sequence, and the similarity between 2 audio is calculated with the ESAM network. We treat the spider score of 2 audio as their true similarity and dynamically sample training data. For each mini-batch, we random choose K anchor audios. For each anchor audio, we random choose M similar audios. For each anchor audio and similar audio pair, we random choose N dissimilar audio. Then, we train this model with a triplet dynamic margin loss. Given an anchor audio A, its similar audio P, and dissimilar audio N, the loss calculation is here, where F is the similarity calculated by the network, and M is the margin function. The margins are dynamic. We calculate the margins by the spider score between captions of audio. After training, we can use the model to obtain a similar audio caption corresponding to the input audio. Firstly, we get the 10 most similar audio in the training site and their captions. Secondly, we use TF-IDF to get the 10 most important keywords and their weight. Finally, we modify the vocabulary probability by the weight of these keywords. We draw 4 conclusions from the experiment. First of all, adding a pre-trained encoder can significantly improve spider score. Secondly, the benefits of data augmentation are significant. Thirdly, the keyword-enhanced decoder can assist the generation of captions. Finally, the tag-enhanced decoder is not effective in this case. We thought this decline was due to the tag prediction error produced by the pre-trained PNN model. There is an example of using the keyword-enhanced decoder. We can see that most of the keywords we selected appeared in the reference, and the keyword-enhanced decoder can make the captions more specific and closer to the caption written manually. Besides, there is an example of using the tag-enhanced decoder. Guided by the tag animal, caption about bird can be generated. Without this strategy, the generated captions are far from the reference caption. This case indicates that the tag-enhanced decoder can keep the generated caption with a reasonable space when the tag is accuracy. Let's summarize this presentation. We propose a method to extract weekly label data from the internet. We also try two ways to introduce similar information. One is tag level, which is tag-enhanced decoder. Another one is caption level, which is the keyword-enhanced decoder. The experiment results show that weekly label data and the keyword-enhanced decoder are effective for our test. In the future work, we will explore the promotion of pre-training with large-scale weekly label data and try other effective way to integrate similar audio captions information into automatic audio captioning tests. Thanks you for watching this presentation.